Assalamu alaikum wa rahmatullah. Today we have another experiment, cooling tower. So cooling tower, mainly it's used for cooling the water. It's special type of heat exchanger and it's known as evaporative heat exchanger. So it utilizes both latent heat and sensible heat to transfer the heat between two fluids. So for example, as you know, for the normal heat exchanger, if you have a water, two fluids or any two fluids, one is hot and the other one is cold, so the heat is transferred between them, but there's a barrier between them, so only the heat is transferred through the change in the internal energy, mCp delta T. While in cooling tower we utilize both sensible heat and also latent heat, so we can utilize the maximum heat transfer between two phases. According to the latent heat, so there is evaporation, leads to evaporation of some of water is lost through the evaporation, and more heat transfer can be lost in the and lead to maximum cooling for the water. We have different types of cooling tower. We have the natural operating cooling tower. So it's by nature, so that means if I put the water from the top to the bottom and air come from the bottom, so when air is mixed with water, so the density of air is become less and it's go to the top, so new air come from the bottom. Also, we have mechanical cooling tower. So this is called natural cooling tower. We have also mechanical cooling tower. So we have two types of mechanical cooling tower. Mechanical cooling tower means that air is driven through the cooling tower by a mechanical force, like a fan. So we have induced cooling tower and we have forced cooling tower. Induced cooling tower, it induces the air to pass through the cooling tower, and the forced cooling tower is force the air from the bottom to the top. So today we have forced cooling tower experiment. So the blower is down and we have the cooling tower. So this is the packing to increase the heat, the transfer area between the water and the air. Hot water comes from the top and pass through the packing. This packing to increase the mass transfer area, and we have the air come from the bottom to the counter current flow, so the water is cooled and then the new water is accumulated here. So this different types of cooling tower. Actually, the water, when it comes from the top, it enters the cooling by maximum temperature, and the maximum cooling the water can reach is the temperature of the inlet air. So we have inlet air has a temperature, and this temperature represents the sensible heat. But we said we utilize sensible heat and latent heat. So the dry bulb temperature, we have dry bulb that represent the sensible, and wet bulb temperature that represent sensible plus latent. So again, the maximum cooling the temperature can reach is the temperature of wet bulb temperature. Wet bulb temperature, because this is the maximum can reach. So this we can say this is the maximum cooling. Okay, but actually due to the heat rejection, water temperature can't reach to this temperature, but it less reach to it. So this we can say this is the range, actual range of cooling. Okay, so this is the actual range of cooling, and this is the temperature of outlet water. So we have Tn, we have T out. Tn is the temperature of inlet water, and T out is the temperature of outlet water. So the difference between them is the range. So this is the range. T in minus T out. So range of cooling, but we said range. Okay, now we said our approach is to reach this temperature. So temperature of inlet with air temperature. This is my approach. Since this is not, I didn't reach this temperature, so the difference between the temperature of water out of the column until the temperature of inlet water is called approach. So approach is temperature of outlet water minus temperature of inlet air wet. Because we said we have two temperatures of air. We have dry and we have wet. So we have also effectiveness. What is effectiveness of cooling tower? Effectiveness of anything is two things: the actual, overall, total or maximum. So we have actual, range, and we have maximum or total. So effectiveness equal range over range plus approach. So this is the effectiveness of cooling tower. Also, we have capacitance of cooling tower. Since we have, we said now, the process is two things. The process is move the temperature from the water into air. So by heat balance, we can say water, the liquid flux or liquid flow rate, Cp delta T. This is represent the change in enthalpy of water equal G, the flux of air, times delta H, change of enthalpy in the gas phase. So here the change only sensible because it's liquid phase, and in the gas phase we have two processes. We have sensible plus latent. So both should be equal if the energy is balanced between them. So the capacitance I can calculate it from G delta H, or I can calculate it from LCP delta H delta T. But it's much easier to determine the capacitance of cooling tower from this part, the first part of equation, because delta T is already the range, and L is the flow rate divided by the cross-sectional of the column, and Cp is the specific heat of the water. So capacitance here equal L Cp delta T. So all these things represent the effectiveness or the characteristic of the cooling tower, factors that increase the criteria of the cooling tower. Also, we have rate of evaporation. When the water, now we said we have a water, okay, let's go for the real example. Now water comes from the top of the column and air comes from the bottom of the column. So now if rate of evaporation increased, that means we have amount of water lost from the water. I don't want to lose my water system. I want to keep it. So when rate of evaporation increase, so it's minimize the effectiveness of the cooling tower. So this rate of evaporation, how can I determine the amount of evaporation? We have air has a certain humidity, and when it exits the cooling tower, it have another humidity. So if the humidity of the air increased, it represents the amount of humidity captured by the air. So we can determine the rate of evaporation from Ma times x2 minus x1. So Ma is the mass flow rate of dry air times x2. x2 is the humidity at top of the column minus x1 humidity at the bottom of the column. Also Lg. Lg is the flux of liquid to the flux of gas. So Lg is also equal LCP over G. So it represents the energy balance of this equation. So this equation, we say this is the energy balance. So L over LCP over G equal to delta H over delta T. So we can represent this curve into something called, this is characteristic curve of cooling tower. So we have 2 points. The first point here represents the top of the column, and this point represents the bottom of the column. So the first point is the enthalpy of inlet, enthalpy of the outlet air and temperature of the inlet water. Here, the second point is the temperature of the outlet water and the enthalpy of the inlet air, because it's countercurrent. So inlet water against outlet air, and outlet air against inlet water. So this point, this line is called as operating line of the cooling tower. And we have also another curve is characteristic curve. This is, equilibrium curve. So this is the equilibrium curve or saturation curve. So it represents different temperature at saturation enthalpy. So this is enthalpy and this is temperature. So we can, here, temperature of inlet water, here is temperature of outlet water, this is range. Okay. Also, we can, if we want to find any enthalpy at certain temperature, we can just extend the line. So here's H, also here's, okay, H. Okay, so this is the enthalpy of outlet air, and this is the enthalpy of inlet air. If you want to determine the equilibrium enthalpy, so just we can extend the line, okay, and go. So this is H star. If you want to determine the wet temperature of the air, so we can extend a line to the equilibrium and then go down again. So this will be the wet bulb temperature. Okay. So if you want to determine the approach, so this is the approach, and this is the range. Okay. Now you have to determine all these things: enthalpy and also humidity. So how can you determine all these things? Using psychrometric chart. Psychrometric chart, it's used to by forecast to determine the air condition, like enthalpy, different. So if you know already any 2 points, 2 characteristics of the air, you can determine the remaining characteristic. So for example, this is a psychrometric chart. If each part of the characteristic curve has special position. For example, now this is dry bulb temperature. This is dry bulb temperature, and it characterized by vertical lines. For wet bulb temperature, it's like diagonal lines, like this. This is wet bulb temperature, wet. Okay. For humidity, we have 2 types of humidity. We have humidity, absolute humidity, and we have relative humidity. For relative humidity, it has a curve like this. So this one is 100%, relative humidity, 90%, and you can decrease as we go down. Also, we have another humidity, it's absolute humidity. Okay, or it's called, as known as humidity ratio, and it's equal to kilogram by kilogram, kilogram of water by kilogram of dry air. Or in some psychrometric charts, you can find it as gram per kilogram. So just make sure you read the units correctly. Also, we have enthalpy. Enthalpy is here, okay, and we have also specific volume. So you can find specific volume like this. What is specific volume? Specific volume is 1 over rho of the air. Okay, So rho is kilogram per cubic meter, so specific volume is cubic meter by kilogram of air. Now, how to use the psychrometric chart? By knowing if you're given any 2 points, you can determine all the remaining characteristics. For example, suppose that in this experiment, we already got the dry bulb temperature of air and wet bulb temperature of air. So this is a dry bulb temperature, this point, and the wet bulb temperature at this point. So since 2 points intersect at this point, so this is my focal point. From this point, I can determine all the remaining characteristics. For example, I want to determine the humidity. So this is the curve for humidity. So I can go to determine the humidity. If you want to determine the specific volume, so this point is located between 2 points of specific volume, so you can determine the specific volume. If you want to determine the enthalpy, so just make extrapolation until you reach this point. So this point is the enthalpy of your point. So that's it. So you can easily find any characteristic using only 2 properties. If you already given any other points, you can also determine the remaining. Okay. So now we already range, approach, effectiveness, capacitance, rate of evaporation, L over G. Okay. One of the main properties of cooling tower to determine its height, okay, and determine what is called number of transfer unit and height of transfer unit. So this part of equation is known as number of transfer unit, or NOG, okay, and this part of equation is known as height of transfer unit, or HOG. So if you already can calculate NOG and you already calculated HOG, so you can design the cooling tower to certain length. So this is the cooling tower. I want to design the mass transfer, how much high the cooling tower should be, so by using this equation. Now in the lab, the height is already given. Height is already given because I know the height of the cooling tower. But the requirement is to determine the K. So in order to determine K, you have to determine the number of transfer unit, you have to determine the height of transfer unit, okay, then you can find K. Okay, now how to find this part, number of transfer unit. Now we need H and we need H star. This part integration, you can use any from the numerical method, you can use Simpson method, you can use trapezoidal method to find the integration between 2 points. So I should integrate along the column. So cooling tower, from the first point to the last point, I should integrate the area behind this point. So let's create a line like this table. First, we have different temperature. The initial temperature, you only have 2 points. You have initial temperature and outlet temperature. So we can say this is the temperature inlet, and here we have temperature of outlet. Here you can assume any intermediate temperature. You can assume it, okay? You can make it at a certain intervals, or you can make it put any numbers, no problem. But make sure that the temperature is between these temperatures. Okay. Now, then we want to find H. Okay. H can be defined using the operating line equation. So this line is y equal a dot plus a1x. Y here is H, and x here is t. So from the t and using the unit operation line equation, you can find H for all points. Similarly, you can find H star for using the equilibrium line. This is line is polynomial, second order. So a1 plus a sorry, A dot plus A1x plus A2x squared. X again, X here is the temperature. So you can use the temperature using the equation of equilibrium line, so to find S star. Now H is calculated, H star is also calculated. So you can find 1 over H star minus H. Okay? Because you want to integrate this one. So in order to integrate this one, you want 1 over H star minus H times dH. Okay? So calculate. Now 1 over H star minus H is calculated. So you can now 1 over H star minus H, and here's H. Okay? So you can integrate the area. You want to integrate the area behind this curve to obtain the number of transfer unit. Now we can use trapezoid method. So trapezoid method assumes that we have a lot of different or continuous of trapezoid. This is trapezoid 1, trapezoid 2, trapezoid 3, trapezoid 4. So the area of under this curve is the summation of this trapezoid. So the area of each one is, we can say, this is y1 and this is y2, and we have x1 and x2. So the area is length times height, and we have two heights, so we can take the average of this height. Okay, so area of each trapezoid A equal y1 plus y2 over 2. So this is the average of the height times x2 minus x1. This is the length. So this is the area of the first trapezoid. By summation, so you can calculate the area under the curve. So here you will calculate. We said this is y and this is x. So now you can take the first cell. If you want to use Excel, you can use the first cell times the second cell over 2 times x2 minus x1. So you can calculate the area of each trapezoid. So this is area of each trapezoid. And then you can find the summation. So by finding the summation, you can find the number of transfer unit. Once you find the number of transfer unit, and Z, the height, is already given from the lab manual, then you can find height of transfer unit. Since you already know the flux of the gas, and since already you know the pressure of gas, this is air, and molecular weight, and A is the density. A is the density of the packing. Okay, density of the packing, and it's already given. It's equal to surface area of the packing over volume of the packing, and its unit is m-1. So you can find the QOL. Now in the experiment, we will do the experiment in 2 times. You can use it in different times as you wish. You can check the effect of increasing water flow rate or water flux. You can check the temperature. You can check the gas flow rate. But here we just will make the test the water flow rate effect. So you will get 2 operating lines, and you study the change of water flow rate on all these properties of the cooling tower. So this is our experiment today, and we already explained every part. So the water comes from the top until the bottom. We have here the sensor, different sensors. This is for wet bulb temperature. As you can see, the sensor is connected to wet cloth to keep it always wet. So this is to measure the wet bulb temperature of the inlet air. We also have here sensor of the dry bulb temperature, and we have the same sensors here again on the top for the exit air, and we have also sensor for inlet water sensor for the outlet water. This tank has a heater and this sensor for water temperature in order to make sure to control the temperature of the water. Also, we have this valve to control the water flow rate through the temperature. And for the blower speed, we just control it from the software. Software is very much friendly, very much easy. So this is the main part before going to the software. So now we'll start how to control the system, a cooling tower experiment from this software. So we have these parts, each part here explain the sensor. So we have sensors for temperature, we have sensor at the water basin, we have also sensor, two sensors at the top of the column for the air, and one sensor at the top of the column for water. Also we have two sensors at the inlet of the water air for the wet and bulb, and also we have another sensor for the outlet water temperature. Also we have two sensors, one for water flow rate using orifice, and another one for air. So as you can see, we can control the air speed from this valve. We can increase it or decrease it. So now the speed of air increase here, and you can find here the pressure drop due to the air speed. Here we control the temperature of the water. We want to make it as inlet for the cooling tower. Then after putting this setting, we just wait for some time until to get stability state, and then take your readings from all your readings, the temperature of inlet water, temperature of outlet water, and different temperature for the inlet and outlet air, and of course record your flow rate, water and air. And after you take your data, you can change the parameter you want to change it. For example, if you want to change the water or change the air, and then wait again until steady state and take your record again, and that's it. So as you can see, it's very friendly software, easy. Just be sure to take the data correctly. Also make sure that you have two temperature, dry bulb temperature and wet bulb temperature. The wet bulb temperature is always less than the dry bulb temperature. Otherwise, you have a problem in your connection sensors. That's it. Then you can take your data and record it, and you do your calculation.